Hi, my name is Interpolation.
Hi, my name is Daniel Jimenez. My name is Ricardo Rego.
My name is Tatiana Perez.
My name is Fernando Pinilla.
My name is Julie Correa.
Well, first of all, good afternoon. We're students of Computer Science of the University of Bosque here in Bogota. We're doing this presentation to present a new topic that it calls numeric methods. So, well, we have divided this video in 3 parts. Each one is composed by 2 persons each group. So the first group is Carolina and Tatiana. They'll be in charge to do the method of Newton-Raphson. Richard and Andres will be in charge to do the method of interpolation of Lagrange. And me and Daniel will be in charge of the method of the secant. So let's begin.
Hey everybody, my name is Fernando Pinilla, and with my partner Daniel Jimenez, we're going to explain about what is the secant method. Well, the secant method in the numeric analysis is a method used to find the zeros of a function by an iterative way. This method contains 2 more methods. The first one is called false position, due to the final analysis of the toleration. And then we have the Newton-Raphson method. We use it to see the mechanism of the iterations that the secant method have to find when the function of x equals to 0. Well, to continue this presentation, let's see the process to know how to resolve a secant method. So, the first step is to have 4 variables. The first 2 variables are 2 points that you select from the graphic to use them to find the root of the function. The next one is the initial function that will have x. That it is used to replace it at the graphic function. And the last one is the toleration of mistake we will need to validate that we do right the exercise. So, the first step is to replace the initial function of x in the graphic function and then find f of x sub 0 and f of x sub 1. Until we do that, we use this formula to find new x. When we find the new result of the new x, we need to replace this result in the x's of graphic function to find the function of the new x. We will keep doing that until the function of x equals to 0. After this, we will need to evaluate the tolerance with each x using the next formula. As you can see, we will need to find that the operation between the new x and the previous x gives us a result that is less than the tolerance to finish the exercise. When we finally got the result of this operation, we select that the last function of x is going to be the final result of the exercise. So that's the process that we know as secant method.
And my classmate is Carolina Correa. In this video we're going to be demonstrating the Newton-Raphson mirror. To begin, we will explain what the Newton-Raphson method is used for. Then we will continue with the formula and the fluid diagram for it.
It is an efficient algorithm used to find the approximation of the series of roots of real forces. It can also be used to find the maximus or minimus of a function by finding the zeros of its first derivative.
The method cannot be used for cases where function derivating by x is equal to 0. There are equations that are complex to solve algebraically. For this, using the Newton-Raphson mirror, is more efficient. This is the formula for this method. This is the formula for this method, where x0 is the point that we already have. F is the function of the point we have. F derivation is f prime, of other words, the first derivation of the function at the point we have. So, now we will explain the fluid diagram for the Newton-Raphson mirror. That is this. First, we plug in the data of the function for x. For the first function of x, the initial point, which we already have, an epsilon, that is the error, which corresponds to that e. That appears in the diagram. In this point, we get it less than the one that we already have. Then it's less than epsilon, and so x0 becomes with the point we just found. Then, to find the new x1, we use the Newton-Raphson formula, which we have explained previously, and it's following. And once again, we evaluate if x1 is less than the new x0, and wherever it is less than epsilon. If it isn't less than epsilon, that is the error, then that is x1, and we have finished the algorithm in this part.
Hi, my name is Andres Felipe, and today I will explain with my partner Ricardo interpolation Lagrange. Interpolation formula to calculate approximate values of f sub x, and consists in replacing function f sub x to be approximated by another function g sub x. May agree that for simplest, operability, etc. The interpolation de Lagrange, it is a way to present the polynomial that interpolation at set of points given. This is a general formula, basic Lagrange polynomials, and expanding the period. And now, an example of application of the Lagrange interpolation formula, the case of one function f sub x, which takes the values 0, 3, and 1 in the 1, 2, and 4 respectively. Find a polynomial interpolation. Half support interpolation, nodes, and base interpolation, and function values at nodes. And this is the process. And this is the result. Thanks for your attention.